In this last definition and example for this section, we're going to take a look at how we can actually attempt to integrate or perform definite integrals on vector-valued functions. Here's the following definition that we have. The definite integral for a continuous vector-valued function is going to be given like this. And we'll notice a similar trend that we've seen throughout this section. To do the definite integral of a vector function, I really just have to do 3 individual definite integrals, one for each of the components. Okay. The interesting thing to note here, though, then, immediately is that the result of a definite integral for a vector function is going to be itself another vector function, right? I'm going to get a vector back. I'm not going to get a number or anything like that like I did back in a Calc 1 class. Okay, so I'm going to get a vector back. Let's go ahead and see exactly how this would work. Okay, I'm going to go ahead and think about starting to set this up down here on, say, example number 3. Suppose that I have my vector function. Again, it's in my I, j, and k form, and I want to go ahead and find the integral from 0 to pi over 4 for my r of t. Okay, according to the definition up above, what that would mean is I have to set up 3 individual integrals, one for my cosine of t, one for this 1 over 1 plus t squared, and finally, one for this sine squared of t dt. Now, all of these integrals here are actually integrals that you should be able to tackle with your knowledge from Calc 1 or Calc 2. I'm going to focus here on the first couple integrals and try to move through them pretty quickly. And I think this last component is actually going to be the trickiest one. Let's take a look here. The first guy, this isn't bad at all. I notice again that I have a nice continuous function, so I can use fundamental theorem of calculus over this interval. And so I know that I'm just going to end up with here the sine of t evaluated from 0 to pi over 4. So if I was to go ahead and kind of just finish this individual part off, I know I'm going to get the sine of pi over 4, that's the square root of 2 over 2, minus the sine of 0, which is just 0. So again, I should just end up then with a final result, square root of 2 over 2, for that first component. Again, I'm creating a vector. This middle guy actually isn't that tough either. It's actually also a simple derivative rule, but it might be one that you have forgotten. Do you happen to remember what you can take the derivative of that spits out 1 plus 1 over t squared? Yeah, this one's a little bit tougher. It's the inverse tangent of t. And here, I would just have to evaluate again from 0 to pi over 4. This is a simple derivative rule that we should have known back from Calc 1, but of course it's possible that you might have forgotten that by now. Here's just a good refresher. All right, so let's see. Now I would just have to evaluate at each of the points. The inverse tangent of pi over 4 creates a 1. The inverse tangent of 0 creates a 0. And so my middle component there just happens to be 1. Okay. For my last component here, this is the tricky one. How in the world do I integrate a sine squared? Make sure that you're careful. You can't do things like say, oh, this is going to be 1/3 sine to the third of t. That's not going to work. And the reason that I know that that's not going to work is because if I take the derivative of this, I don't get back to where I started. So I need to make sure that when I do the derivative, I do indeed get back to this original thing. And here that won't happen because I'm going to have to do a sine squared of t. I'm going to bring the 3 down to the front, lower the power by 1. But then I'm going to actually have to chain rule and multiply by the derivative of a sine, which is a cosine. So I don't actually get back to where I started. Here what I'm going to actually have to make use of are some trig identities. And these might be trig identities that will be useful to know moving forward. These were some important trig identities that we use whenever we see things like cosine squareds and sine squareds in our integration. I always can replace these values with the following. Okay, so I can replace a sine squared of t with a 1/2 times the quantity, 1 minus a cosine of 2t. And over here, I can replace the cosine squared with the same stuff, but just with a plus sign. So it's nice because it almost feels like one thing to memorize there. And I always remember that the sign has the subtraction. So sign subtract. Okay. So if I was to make use of that here, I can then think about this as the integral of 1/2, 1 minus the cosine of 2t. The advantage to this is that now I can think about pulling, say, the 1/2 out of the integral, and these other pieces are actually fairly easy to find antiderivatives for. Let's see, I'm going to have 1/2 times antiderivatives of each of the other pieces there is going to be t. And then over here, let's see, I'm going to get something that's kind of like a sine of 2t, because if I do the derivative of the sine of 2t, I'm going to get cosine 2t. Ooh, but then I would have also needed the chain rule, right? If I took the derivative of the sine of 2t, I would have gotten cosine of 2t times 2. But I don't want a 2. So what I'm going to do is I'm going to front load this with a 1/2. I think then that would work. Okay. Then I can just evaluate this from 0 to pi over 4. If you're struggling to see how I kind of did that integral right here, there's two ways that you could try to assist yourself with that. One, you can double check by taking a derivative of what I have, see that it gets you back to where I started. But you could also attempt to try to do this with a u substitution in case you're struggling, where you could let u be equal to 2t, and then you could go ahead and perform a substitution there. All right, if I was to go ahead, though, and finish evaluating this guy, let's see what I would end up with. I'd have 1/2, let's see, I'd have pi over 4 minus, let's see, if I plug in pi over 4, it's going to be sine of pi over 2. So this is going to be minus a 1/2. And then I'm going to have minus, and I'm going to have 0 minus, let's see, sine of 0 is just 0. Okay, so yuck, I get this vector. If I simplify that down, I'm going to get square root of 2 over 2, 1, and then it looks like something like pi over 8 minus a fourth. And I'm just going to leave it like that. That's an exact answer. So I can complete definite integrals, okay, by simply just doing definite integrals for each of the individual pieces here. You can also do indefinite integrals, although I'm going to leave that as a homework question and as well as some worksheet examples for you to work through to try to think about what you're going to have to do with this plus c that typically popped up. Okay. Of course, as you have questions about that, you can feel free to let me know. Okay. One thing that's often, though, kind of confusing in general about this concept of integration is like, what does this have to do visually with the picture, right? If I was to go to the 3D plotter, what's happening when I do an integral? Well, for the moment, as the note states up here, we're going to kind of hold off on that physical or graphical interpretation of what's going on, and we're going to save that for the last section of this chapter in 2.6. For now, we just need to be aware of how to actually complete the integration and to note that the answer to the integral of a vector function is, again, another vector function, or another vector.